Good afternoon, everyone. Did anyone confirm, am I audible?
Yes, sir, you're audible. Good afternoon, sir.
You are audible.
Okay, thank you. Okay, so welcome to the third session of this workshop. You've already gone through the two sessions, one for the basics NumPy and basics of the Matplotlib library and bit of the SciPy library as well. And today morning we have seen one algorithm that we have implemented using NumPy libraries, that is k-means. Okay, so agenda for this particular session will be implementing the another machine learning techniques which is very popular in machine learning, and that we are gonna see here. First, we will start with the linear regression technique, and then we will move to the kernel regression, and in the last, we'll quickly go through the regularized version of the linear regression as well. Okay, so should we start now? Or if you have any questions, any doubts, you can ask. Otherwise, we should start. Okay, so let's get started. Yeah, one more thing. If you have any doubts, you will be provided some time to ask your doubts. If you have if you have doubts regarding particular code that we gonna use here, then you can please unmute yourself and ask. Otherwise, keep your mic muted every time. Okay, so let's begin. Let me share my screen first. Okay, so is my screen visible?
Yes, sir.
Yes, sir.
Okay, you can see that collab file, right?
But we do not have this collab file.
Yeah.
I've added this collab file in the same folder that you have been provided yesterday.
It is not updated, sir.
It's not available.
No, I've added that file there. Can you please check now? Refresh that. I've added that file.
I'm
There.
refreshing right now.
Okay, so let me check once more. I remember I checked it. Can you paste the link of that folder here? I check once more. Either way, I've added that.
You are saying collab slides day 2, right?
Yeah.
So it is not there actually.
Yeah, sir. And day two, do not pay.
Okay, so let me add right
Sir,
now.
only K means is there.
Yeah, okay, I can see that. Okay, let me add one. Give me 1 minute. Okay, please refresh now. I've added it. So are you going to code along with me, or are you planning to do code after the session?
Along
Better,
with you, sir.
I will code along with you, sir.
better you can focus on the session, and then after that you can write by yourself, not looking at the answers and all, not looking at the solution. That
Yes,
will
sir.
be a better way. But if you prefer to doing along with me, that is also fine for me. Okay. So you can access that file now, right? To make a copy of that, and then you can start coding there. Okay, thank you. Okay, so now you can see the collab file, right?
Yes, sir.
Okay, so in this particular session, we are going to implement a linear regression techniques. Then we'll go for kernel regression, and after that, we quickly go for the regularized version of that. Particularly, ridge regression we'll look for, not for the lasso, because lasso don't have any closed form solution. So let us start. And uh, I hope you all know the linear regression techniques, and this is the very first supervised learning algorithm that we come across in the machine learning techniques course. And I hope you all go through that and you are aware of the techniques is what techniques is. So I will go through the techniques, but not in details. I will go through briefly about the techniques, whatever is required for this session. I will briefly discuss that. Not I will not gonna derive any formulas. I'm not gonna do any proof here. Just I will touch upon the actual algorithm, not in the details. Okay, so as you know, this is the supervised learning algorithm. So supervised means you have access of the training
Can
data
you
set.
please switch off the dark mode?
Dark mode. It's only white mode, right? Not in the dark mode.
Showing it in dark mode here.
Is it in the dark mode?
No, sir, that's
No, sir.
white and white.
No, sir.
It's okay for me.
Yeah, I think it's okay for me as well. Can you check from your side? It's okay for me.
Okay, I'll reconnect.
Yeah. Okay. So as this is a supervised learning algorithm, we have access of data, and data means training data means you have the feature metrics and the corresponding labels, right? And that's because we call it a supervised learning, because with each and every example there is associated label with that. Okay, so in this particular session we are gonna stick with the conventions of X, which is a feature matrix of the shape d cross n. So if there are n training examples, and there are n training examples, and all those examples are coming from the t-dimensional space. That is there are d number of features in the data set. Then the matrix that we are gonna use here is of the shape d cross n. So capital X here denotes the feature matrix of the shape d cross n, where it contains the data points. Okay, so n are the number of examples and d is the number of features, and small x is here denoting a particular example. Right, so each xi is coming from d-dimensional space. So every example takes d features, and there is associated label with that. So this is training data set we have access to. Now, so we are storing the labels in a vector. So by 1 to by n are the associated label of those x1 to xn examples, and we are storing them as a column vector. And remember this, as this is a of shape d cross n, each column here is denoting one particular example. Let's say the last column denotes the nth example, the second column denotes the second example, and so on. Okay, and if you have done the MLT course in the last term or the very first term, then we have used slightly different convention there. We have used n cross d, but it's just a matter of convention. It doesn't affect your algorithm at all. It's just the different variation, different version of the same formula. That's it. Okay, so it's just a matter of convention. You can stick to any of these, but you just fix whatever you are comfortable with. I'm here using d cross n matrix. You can, if you want, you can use n cross d matrix as well. It doesn't matter. Okay, it's just a matter of convention, right? So this is the data we have been given. So for this particular coding, implementing the algorithm, we have generated this training data set. So let's see what this is. So for setting random seed, we have used np.random default RNG. You have already seen that this is a module in NumPy library, which actually skips, which is used to generate the random numbers from different distributions, like generating integers or generating samples from the normal distribution, from uniform distribution. So there's one module in NumPy which is called np.random.default RNG, which actually have different functions to generate different numbers. Now we are setting a seed here at 101. It makes sure that whenever we run this particular cell, the number that is generated is same every time. Every time we run this code, we get the same numbers, not the different ones. Okay. Now, so in our training data set, we have generated using the code np.arrange. So let's see what this does. So So if you look at np.arrange, it actually gives you the sequence of consecutive numbers starting from 0 to the endpoint. So endpoint I've decided to 5. So it will give you the consecutive numbers starting from 0 to 4, 0 to 5, 5 excluding. So it will give starting from 0 to 4 with a step size of 1. So step size here it's 1. By default is 1. You can set by yourself as well. So let's say I'm to generate numbers from let's say 10 to 15. Let's say 10 to 50. So I will just set the initial point at 10 and the end point at 50 and the step size as well. So by default it's 1. So it will give me the sequence of numbers, consecutive numbers, equidistant number from starting from 10 to 50. And I can also set the step size as well. If I take the step size of 3, then it will take the step size of 3. Now it will generate the number from 10, then 13 up to 50 with the step size of 3. So that's how this function I've used to generate the number. So I've generated number from -2 to 2 with the step size of 0.01, right? So this is my one feature only, and I'm considering the dataset containing only one feature. You can extend these notions to any number of features as well. But for this particular task, I'm using only one feature. So training dataset contains only one features, and those values are coming from -2 to 2 with the equidistance, and the distance is 0.01. And I've reshaped into 1 cross 1 into -1. So 1 means there is only one row. Remember, we have taken the shape of the matrix D cross N. So D means number of rows. So there is only one feature, D is equal to 1. So I'm setting the rows at 1, and -1 will make sure that it will automatically fix the number of columns for hours. Okay. So now, so this is my data matrix, and the corresponding labels I've generated using this formula. So remember, in the linear regression, we assume that the labels are associated with have some relationship with the features. Here, in that case, the labels are X trained. So the labels are coming using this formula where it is has some cubic relationship with the features. Right. So this is some cubic relationship with the features, and again plus 3 times of x square plus 4 times. So this is the relationship between the features and the data. Okay, and the label. Sorry. Yeah, so it has some cubic relationship, and I've added some noise into the data set, right? So we have assumed that labels have some relationship, but some noise associated with each and every example. So that noise I'm assuming is coming from the Gaussian distribution, Gaussian 0 with the variance 1. And because for each and every example I have to add the noise. So how many noise I'm generating, how many bytes numbers I'm generating, the same as there are number of examples. And number of example I can get access from taking the shape at the 1, because it's the shape of D cross N. And then again I'm because all this gonna be of the shape D cross N, I'm again setting the shape of this to D cross N. D is here is 1, and it will taken care of explicitly. And then I'm taking transpose just because by actually is a column vector. Here it's gonna be 1 cross something 1 cross N. And so to make it n cross 1, I'm just taking the transpose of this thing. Okay, so let's check what x train and what is the shape of this thing. So if I look at of the x train dot shape, so it's of 1 cross 400. So it means that there is only one feature that we have generated using this thing, this np.array, and there are 400 examples in the data set. Right. So similarly, you can check the shape of y as well. Right, by train usage. Okay, so the shape of by is a column vector where there's 400 example and the associated label for that. Okay, so any doubt till this point how I've generated the training data set?
Excuse me, sir.
One doubt, sir.
Yes.
Why can't we make the number samples comma features?
No, you mean that in the X matrix you can take n cross d, right?
Yeah, okay.
Yeah,
Means
yeah.
we
You can go in that manner as well. It's just the matter of convention. Whatever you fix, it's okay. it's not gonna change your algorithm at all.
We had followed decross n in course.
E cross n in this particular term, and if previous term we have used n cross d, but it's just a matter of convention. It's nothing else. There is a different version of the same formula will come up, right? If you have used this x, there it's gonna be x transpose. That's it.
Yeah, yes.
Excuse me, sir.
Yes.
Instead of transpose, like in the reshape also you can do, right? Like
Yeah.
minus
Again,
one
yeah,
comma
sure.
one.
Yeah. Again, you can rather than doing transpose, you can reshape it into one comma minus one comma something.
Yeah.
I mean the
Yeah,
n comma
could you
one. So
please
n will,
explain RNG to normal again?
sorry, RNG dot normal, is it this one?
Yes.
So this is the module in the NumPy which actually used for generating different numbers, different random numbers from some different distributions. So okay, so RNG I'm setting this module. So this module times dot normal actually gives you the sample from the normal
Normal
distribution,
distribution with zero mean
the
and one
mean
standard
and
deviation.
one variance, and how many samples I want. Because I need to add the error
Okay.
term or bias term into each and every
X
example. So
number
this
of
number
examples
of
in X
examples
string.
I'm taking out from that Gaussian distribution.
Oh, thank you.
Okay, so let's check the shape. Let's try to plot it as well, because we have only one feature, right, and one label, so we can draw it into the two-dimensional space. If we have more than two features, then it's hard to visualize it. But in this case, we can visualize it. So let's make the scatter plot of this. So for making the scatter plot, you want the numbers that you have on x-axis and the y-axis. So on the x-axis, I'm taking the data points, the feature, and on the y-axis I'm taking the label. So on the x-axis I have x train, and on the y-axis I have the y train. So if you plot this diagram, so it's coming something like this, right? So actually it doesn't have any linear relationship, but the labels are associated with some relation to the features, right? But in this particular case, we know this is not linear regression is not gonna do good for this particular data set. But if we have large number of features, you cannot draw this relationship. You cannot find out this relationship by looking at the scatter plot. So we start with the linear regression, and then we'll go for the kernel regression for the same data set. Okay. So on the x-axis you have the features, and on the y-axis you have the corresponding labels, right? So you can see that the values of x are coming from -2 to 2, and the corresponding labels have some relationship with this x, right? So if it is 0, then it is for 0 it will be somewhere around 4, because at 0 it will be 0, 0, and plus 4, and obviously some noise added to that point. Okay, so that's how your data set is distributed. So our task is to apply the linear regression model on this data set. Okay, so similarly, I've generated the data set as well, and test data set is again coming from the same distribution. So I've generated the same numbers from -2 to 2 with some different step size to make sure that there are different numbers in test data set. And the labels are again associated with the same manner, because we always assume that the test data set and training data set comes from the same distribution. So it has the same relationship that we already designed, and with some noise added to that. Okay, so it's nothing different. It's just like training data set. Okay, now so let's quickly look at what the linear regression model is. So actually, our task is to predict. Sorry. Okay, so our task is to design a function, a mathematical function, such that we give the input to that function. It gives some output. Output means the prediction values for that. Can you please mute yourself?
Hello.
Hello. Yeah. Okay. So so our task is to design a mathematical function that whenever we provide some data point to that, it gives the prediction for that. Okay. So in the machine learning techniques, we usually call that mathematical function as a model. So we can come up with any type of function for that, right? Some sine function or some cosine function or some other trigonometric function. But we have already seen that we always stick to the linear functions, right? We don't go for beyond that, just because we can always have memorizable function for that, where each data point just gives the actual value for that, and we can achieve training error zero, always achieve training zero training error for that. So we always stick to the linear functions, and so we assume that this is the function that we are gonna fit for this particular data set, where these w1 to wd are a parameter that we are going to find out, and these x1, x2, xd are the features. So upper script actually gives you the features, and so this can you please mute yourself, otherwise.
भागवत सुन के तुम्हारे अंदर का छू चेंजेस तो दिखा दे, नहीं दिखाते तुम।
Okay. Okay, so we are assuming this is the this is the function that we are gonna learn. So we have to find out these parameters, and so these are x1 to xd are the features. So this particular can be written x transpose w. So remember, x transpose was the data point and w is the weight vector. So it's again a column vector of the shape n cross t cross 1, where the entries are w1 to wt. Okay, so it's in a hyperplane in the d plus 1 dimensional space, right? So in our case, we have only two-dimensional space. So one feature means this particular function gonna be a line in this in this two-dimensional space, right? So some line we have to learn, and we want line to explain this data set, right? So now we have to make sure that these lines need not necessarily pass through the origin, because the data set can be anywhere, distributed somewhere else rather than origin, along with the origin. So we want to make sure that this hyperplane actually doesn't pass through the origin. We allow it to pass through and to have any intercept on the y-axis or any other in the three-dimensional on the z-axis as well, right? So for that, what we do, we add some bias term or say intercept term in our model, and the corresponding label we just set it to 1, right? So we have the point x1 to x, so it's gonna be xd. So if we have point x1 to xd, we just add one features as well, which is a constant feature, and we set the value equal to 1, just to make sure that we have added the intercept term in our model. So now our model is gonna look like x transpose w. Now x has d plus 1 features, and w again will be d plus 1, where we have added w0 to wt. Now, so if we consider the intercept term as well, now the capital X, the data matrix gonna be of the shape d plus 1 times n, with n examples and d plus 1 feature, because we have added one dummy features as well, and the w gonna be of the shape d plus 1 1, where d plus 1 are nothing but w0 to wd, and our task is to find out these d plus 1 parameters, right? Okay, so for going moving forward, let's add dummy features first. So remember, in this x train and x test, we haven't added the dummy features yet. So for adding dummy features, what we have to do, we have to add one to each and every examples, right? So here, in our examples, so these rows represent the features value. So we will add one row as in the starting or in the last. We will fixing at the starting. So in the starting, we will add one row where all entries are 1. It makes sure that every data points, the dummy features for every data point is 1. Okay. So what we will do, we'll add one row in the starting of the matrix X train. Okay. So for that, what we do, we'll let's generate a vector. Let's call it dummy feature, and it's just a vector of 1. So there is one function in NumPy which is called np.ones. What is that? It's create in vector an array of all entries equal to 1, and how many ones we want, the number of example, right? So it's gonna be x train dot shape 1. So how the n, right, number of examples, that many ones we want in that row. So this will give me a vector of all entries equal to 1. If you check this is gonna be a vector of all entries equal to 1. So if you check this, is an array with all entries equal to ones, and the shape gonna be 400 because we have 400 examples. Now we have to add this row in our dataset X string. So how can we do that? Is there any function? Concatenate is one function, or any other idea for that?
A dummy.
Stacking. Yeah, stacking is also the one way to do that. So let's do what row stack does. So I'm calling that matrix now X. So I'm just using np.row stack. You can use concatenate function as well. I'm using stacking. So what row stack does is actually takes two arrays and stack them row wise. Row wise means that let me explain this here. So let's say you have an array np dot array, only one row you have 1 2 3. So this is an array of one row. I mean the row vector you can call it, and let's call some array as well. Let's call this 3 4 5, and there are two rows. Assume that 9 6 7. Okay, so there are two vectors. Now we about to concatenate row wise. So what row stacking will do? Row np dot row stacking, np dot row stack will do. So one point you need to remember, whatever you are stacking, whatever arrays you are stacking, you have to pass through using tuples. So I'm taking tuples here. I'm passing A and B, and what it does is stack these two arrays row wise, right? So first it will take the first array, which is A 1 2 3, and then stack it with B array. So B takes 2 3 2 3 2 4 5 9 6 7. So it will stack row wise, right? So that's what we want. So we have to make sure that these number of columns should be same, right? If there's no number of columns are different into these two arrays, then it won't stack. So if you only take two columns here and three columns here, then it will show error, because number of row number of columns must be same to stack them, right? We are stacking two row by. So that's how the row stacking works, and that's what we want. We want to add the row the dummy features into the our X vector. So I will pass this as a tuple here. I will pass uh, here as a tuple. So the first array will be my dummy feature, and the second array gonna be my X string, right? So it will do me the work that I wanted. So if you look at the X here, now X, if I check the shape of X, now it's gonna be shape of 2 cross 400. So there are two rows. First row denotes the feature, the dummy feature, and the second rows denote the first features that we already have, and there are 400 examples, right? Now we have to add the dummy feature into test data set as well. Let's call it as xt. The same thing I'm gonna use row stacking. You can use concatenate function as well. Okay, so here again I will pass as a dummy feature, because in the training test data set there are different number of examples. So I cannot use dummy feature here. So I will generate another vector of ones. Now the shape of that will be the test data set, right? Test dot shape, the number of example in the test data set. So this is my first row, and the second that I'm gonna stack it with the X test. Okay. So I've added the dummy feature in the both training data set and the test data set. Okay. Now I have the data set with me. I have this model to learn. So how to learn this model? So to find out these parameters, we need some metric which can actually define my loss associated with the prediction that I made, or the some metric I need to define. And in the case of linear regression, we use the sum of squared error. So for ith training data point, I assume the error will be actual levels and the predicted levels. So actually we have been given the training data set, and the predicted that we are modeling, that we are predicting using that model W transpose Xi, right? So this is gonna be the error that is incurred by the ith example, and the total loss by the training data set or the training set gonna be the sum of squared error. So I will take error associated with each and every example and the sum it over all such examples. So this is going to be the total loss of this training data set. Now I want to minimize this error, right? Because this is the error that point incurs. So I want to minimize this. Okay. So now if you think this this as a function of w, and I'm to minimize this. It's just an optimization problem, and so this loss function can be written as x transpose w minus y transpose x transpose w minus y, where x is capital X is the data matrix, w is the weight vector, and by the label vector, right? So you can verify it as well. And 1/2 I use just for the mathematical convention, just because I take the derivative, that 2 comes out, and just to cancel it out, I taken 1/2. It doesn't matter at all. Okay, so this is my loss function. And this is a function of parameters w. Okay, so I have to minimize this. So there are two ways to minimize this. One is called of the normal equations. Remember, this is a quadratic function, right? Quadratic equations of in w. So it's a convex function. I can use the normal equation where I can set the derivative of this loss function with respect to w to 0. And there's another method which is called gradient methods. And so both we are gonna look here. So in the first method is called normal equation, where we take the derivative of the loss function with respect to parameters. So parameters are w here. We will take the derivative with respect to each w0 to wd. So in the vector form, it will the derivative of this loss function gonna be xx transpose w minus x. I'm not gonna prove it here. You can check it out. You can do it by yourself as well. Okay, so this will be the derivative of this loss function, and I have to set equal to 0. If I set equal to 0, it will give me the optimal or say the minimal value, where it has the loss function is the minimum. Okay, if I set equal to 0, the w is gonna be xx transpose inverse xy, right? So in the most of the cases, this inverse need not to exist, just because this particular matrix xx transpose need not to be full rank always. So we always use pseudo inverse rather than inverse, because if it is invertible, then pseudo inverse is nothing but the inverse itself. Okay, so any doubt till this point in the theory? It's just a theory I just mentioned here.
No.
Okay, so our next task is to find this weight vector. So what I will do, I will define a function that will give me the weight vector. So I'm defining weights. So training data set we always have, right? Otherwise, there is nothing like modeling in the machine learning if we don't have the data set. So we have been given data set. Now we have to find the weight. So weight is just this expression xx transpose inverse xy. So I have to write down this expression as it is. So it just return me the xx transpose inverse. So for finding inverse, there's for doing any linear algebra functions, to apply any linear algebra function in the NumPy, there is one module called np.lin_else. So it is np.linear algebra. In this module, you can perform certain linear algebra function like finding transpose, or finding determinant, finding inverse, pseudo inverse, or solving the system of linear equations, or say finding eigenvalue or eigenvector. So different functionality of linear algebra are performed. For performing those functionalities, NumPy has a module called linear algebra, np.linear algebra. Okay, so for finding inverse, there is one function in this module which is called p inverse. For inverse, it is inverse itself, and for finding pseudo inverse is p inverse. For what matrix I need to find the inverse? Xx transpose. So it's just x multiplied by x transpose, right? So this will give me the inverse of xx transpose, pseudo inverse of that, and then it multiply by with x and y. So it will just return x and y, right? I've just written out this expression here, nothing else. Right? So in our case, if I found w, let's call this function for our data set x and the training variables. Right. So remember, we have only two weights, W0 and W1, because there is only one feature. So this is the bias term, and this is the weight vector associated with the first features, right? So this we got using our data set. Let's call it W, because I'm to use it again for making prediction and all. Let's call it W. Okay. Now I have to write the function to make predictions. Right. Now we have a model. Sorry.
Isn't it be
Should
extreme?
use
It will
extreme.
be x. No, we added dummy features.
Yeah,
Okay,
because in the dummy, the
Okay,
one
got it, sir.
which I've added dummy feature is x, not the x-ray. Okay, if I use dummy x10 itself, then there is only one weight vector come out, right? Okay.
Okay, sir, got it.
Okay, now I have the weight. So I've learned the weight vector. So I have the model with me. So I have this values W0 to WT, and to make the prediction, we have the function with us. I just put those values here and to get the output. The function will give me the output, right? So let's say some test points comes in, then I just put that test point in the for this function, and this will give me the output. So the prediction for making prediction for any point is just the x transpose W. Now we have W, and just take the dot product of those two vectors, right? And for a data matrix X, let's say we have been given some test data matrix. To make the prediction for every data point, I just take X transpose W, because remember in the X, every column represents the data points, right? So in the X transpose, every row now will represent my data points. If I take the X transpose dot W, then every element will be what? The row times weight, right? Row times weight, and the row will be what? My data points, and times weight will give me the predictions, right? So for making prediction, it's just the X transpose W. Let's say I've been given. So let me write down the code first. Let's call this predict, and it takes the data matrix for which I want to make predictions, and the weight vector, the weight vectors. Okay, so what it should return? It just X transpose W, right? Because remember, X transpose, we are taking convention of B cross N. So each column represents a data points, right? So X transpose, in the X transpose, each row will be my data point. So very first element of X transpose W will be the first row of X transpose and the W vector. So that's gonna be the prediction for the first point. The second element will be the second row times the weight vector. So it's gonna be the prediction for the second point. Similarly, for the nth point, it's gonna be the nth row of the X transpose times W. So it's the prediction for the nth point. So this gonna be a n vector, and in this vector, it will give me the predictions for all n examples, right? Is that clear?
Yes, sir.
Okay. So for our case, we have the training or test data set. So let's find out the predictions. For prediction, let's call for X first, and using the W vector. This is the predictions for this is the prediction for our training data set. Let's make predictions for test data set as well. So let's call it XT now. So this will give me the predictions for the test data set. These are the predictions for the test data set. Okay, I'm muting everyone.
So, sir,
I muted everyone. Please unmute
yeah,
yourself now and go.
yeah. Up to what extent of the size of X we can means go through this method of normal equations? Like for large number of n, it would be difficult.
Yeah, for large number of n, this is gonna be very computationally lengthy. If there are
Yeah,
lots
yeah.
of features,
So,
lots
so
of examples.
yeah, like here 400 means that size was
Very less. This is
yeah,
very less.
and the dimension was also one. So
So
yeah,
gonna work. But in the most of the practical scenario, we don't prefer go through the normal equation just because this becomes very computationally lengthy. We go for the gradient methods that we're gonna look for now. Look for that. Okay. Okay. So let's call it by head now. If I want to use it in for some other call, let's call it by head for the training data set. Okay. So you can make predictions for both training data set and the test data set as well. Now I want to plot this weight vector as well, because now I have the weight with me. That W is my weights. I want to plot this weight vector. So how I can plot this weight vector? Let's do that. So let me first plot again that data points. It's gonna be train by train. Now I want to plot the data weight vectors as well. So plotting weight vectors means I want to plot this hyperplane. So in our case, this hyperplane is nothing but a line. So I want to draw this line, right? So this particular line I want to draw. So in our case, it's just W0 plus W1x, right? Where x is our data point. So what I will do, I will take, I want to draw this line. So I want to take 2 points and just add those points to plot those, right? So remember in this particular function, in this particular function, I will take these points -2 and 2. And for -2, the function by value will be, I will calculate from W0 plus W1x. Then I will have 1 point. And similarly for the second point, x2, I will take as 2. And the corresponding by will be, I just put that 2 into the function W0 plus W1x. And I will take the by value as well. Now I have 2 points for corresponding to this value and this value. I just add those values, right? And I've done. I've drawn my hyperplane as well. Okay. So for doing that, I have to get access of these limits. So for that, the Matplotlib have one function which is called access get GCA. So let me call it plt.gca. What GCA does, it actually gives the current axis to you. Okay, so these current axis I'm using, so it will give me the current axis, the axis of the current axis. Okay, so what x values I'm interested in? I'm interested in the limits, right? -2 and 2. So x limits. So axis dot get limit will give me. So this will give me this limits -2 and 2 limits of the x-axis, right? So that's what I want, and I will just store them into an array. Now I will take the corresponding by value. So corresponding by value I just put in the function, that function W0 plus W1x, right? So this will be W0 is what? From the W vector I've taken the very first value. This is the W0, and we have W1 times the x values, right? Okay, so these are my x values -2 to n2, and corresponding by will be in this array. Okay, so plotting is just very simple. I just use plt and those x values and y values. Plt.plot x values and y values, and I can make use of red line using. Right? So this is my weight vectors now. Okay. So any doubt how I draw this particular hyperplane or particular line?
Sir,
What is this GCA?
GCA
plt.gca.
so GCA actually stands for get current axis. So it actually, if there is no axis defined earlier, then it creates a new axis. Otherwise, if there is only some axis defined, so remember in scatter plot we already have some coordinate system. So it get access of that system. Okay, from using this, it will take only this axis, x-axis and y-axis, the configuration of this particular coordinate system.
sir, why
Actually, it
we
is
call
getting
it?
the x value, right? X value from the x train.
Yeah, so in x values, if you find out what are x values, so let me code it. X values actually this -2 and 2, the limits of the x-axis. So it's -2 and 2. So these are the limits of x-axis. So somewhere -2.1955 somewhere in this axis. And similarly, the last limits for x-axis is 1.85. Similarly, by values is just operations on this array, right? We have already seen how to do operations on array. So this is the scalar multiplications, right? We have scalar and the scalar multiplication with an array plus addition of one scalar as well. So you have already seen in the yesterday session. So this will give me the corresponding values for these two endpoints, -2 and 2. And once we have these 2 points, I just add a line there. Okay.
So, sir, this line is only for weight vector, not it's for x and y. Huh?
We have this model, right? W0 plus W1x.
Yes, yes.
I've drawn this model here, this function here, W0 plus W1x. For drawing, I need just 2 points on that line, right? Once I have 2 points on that line, I can just draw a line passing through that point. So for using that, I've just taken 2 points, one at -2 and other at 2. and add it to
So, sir,
and
sir, this W0 and W1 means for a single line, W0 is the intercept value and W1 is the slope of that line.
yes, yeah.
So adding these two and plotting, so what is it showing? I'm not getting that.
Okay, so actually I'm
Y
drawing.
equal to mx plus c, that red line, it becomes y equal to mx plus c.
Yeah, so this particular line, this is your label, right? By this is your by plus W0 plus W1x. So this line I am drawing.
Okay,
This is
okay,
your model,
okay.
right?
So you are drawing the model itself.
Yeah, model itself. Drawing weight vector means I'm drawing the model. It's easy in the two-dimensional because my model is lying in the two-dimensional space. If it's more than 2 dimensions, then it's hard to draw your hyperplane there. But in our case, it's easy to draw. So I'm just drawing. This is how your weight vectors look like. So for making prediction, let's say I'm to make prediction for x equal to 0. So prediction is somewhere here on this red line, and maybe the actual level have some point here for x equal to 0.
No,
That's
sir,
okay.
we better can
One
say,
thing, sir.
sir, we
You are
better
saying
can say that we are means drawing that y prediction value with respect to x.
Yeah, x-axis. Yeah. That is what model is, right? Y equal to W0 plus W1x.
no.
That is for any x, it gives
You
the
were
prediction.
saying we are plotting weight vector. So are we plotting weight vector or we are plotting y predict?
No, actually, weight vector is not plotting weight vector. We are plotting the hyperplane, that model itself,
Correct.
right? So let me call it plotting the model. Plot.
So
Okay.
can we draw a quadratic equation graph also as a hyperplane? For example, y wells equals to W naught plus W1 into x wells plus W2 into square of x wells.
Yeah, if there is some other relationship, then you can also draw that in the plotting. PLD.plot has that functionality. You can even draw sine function, any function you can draw in the two-dimensional space. There's
No,
no
I was
restriction.
talking about creating the hyperplane. Y wells
Yeah,
equals to W naught.
hyperplane in the two-dimensional is easy to plot, but in the higher dimension, it's not easy. Here it
No,
is
can
only
we?
two-dimensional space, then we can easily draw it, plot it. Okay. Okay. Since
Can we try with 3 dimension? Is it okay?
even in three-dimensional, we can use, but not preferred using matplotlib library. There's some other visualization libraries like Sinbon and all. There it is preferred for three-dimensional, but you can do is matplotlib as well for drawing three-dimensional. Okay. So now you have model, you have the predictions. Now you have to evaluate your model. So for evaluation, what you do, you define a metric which is called root mean squared error. It's just nothing but the root over the predictions, right? So this is your error for ith data point. So you take the sum of all squared errors, not sum, the mean of those squared error, and then root over that, right? So this is your root mean squared error. So for defining this function, it's easy task. I can just define let's call what to call it, define, let's call it loss. Define loss. It takes the parameters actual level by and the predicted level pi hat. Okay, so what it will do is just return this expression. So it's just the mean of this by minus by hat square, right? So it's just the mean of np dot mean p dot mean of what, mean of by minus by square. So by minus by hat 2 square. It will give me the mean of y minus y square. So I have this inner term now with me. I have to take the square root of this. So this has np dot square root. Np dot sq rt will give me the square root of this particular function. Is that fine? So np dot mean of this. So it's giving the mean of y minus y hat square. So this term, this internal term I have, and then I'm taking the square root of this thing. That's it. Right. So let me check the loss for the training data set. So remember for the training data set, the prediction I was calling as by hat, right? So by hat is the prediction for the training data set. So what will be the loss for the training data set? I can make use of this function. The actual level is by train, and the prediction I call it as by head. So the loss in that case gonna be 4.47 loss I'm incurring for the training data set. Similarly, let's find out the loss for the test data set. Let's call it by t hat. The test data set prediction, it's gonna be predict for predict takes what that x test, right? X test and the weight vectors w, and the loss will be what then? Loss will be my by test, right? By test and by t test. By t. So this is the loss for the training data set, and this is the loss for the test data set. Okay. So any doubts in the normal method?
np.linarc.log
np dot
linarc.non.
yeah that if this is the square norm, right? The norm 2. Yeah, that also you can use. So this is the normal method. Next is called gradient method. So one way to find the optimized value of the loss function or the optimization problem is using setting the derivative equal to 0. Others are called the gradient methods, which are mostly used in the practice because this sometimes becomes very computationally lengthy. So what is gradient method? So what is gradient of a function? Let's say any function you have been given the gradient at a point x. What does it give? It gives the direction of the maximum change that maximum change in f at that point. Let's assume some parabola. Okay, you are at a point. If you find the gradient at that point, then the gradient gives the direction where the function takes the maximum, where the function changes is maximum, right? So and what we want to move into direction of the minimum change, right? We want the minimum value of function. So what we do in the gradient descent method, we start at a random value of the variable, which is w here. So we will start at a random w, then we will find the gradient value at that point. Okay, so gradient gives me the direction of the negative change. So what we do, we just move into the negative direction of the gradient to make sure that we are moving into the least value of the function, right? So this is called the gradient method. So we start with some random value w, then we'll move into the negative gradient direction. So let's say for kth iteration we have the weight vector wk. Now we find the derivative of that loss function with respect to w and at wk and move into that direction. So this particular w in the next station wk plus 1 gonna be your w my w we move into that direction, gradient directions at that point, right? So alpha is the learning rate. It decides how many steps you take in that directions, and it depends on the behavior of the loss function. So alpha is a hyperparameter here. Generally, it's set manually, and we won't go much about the learning rate. There's different ways to set learning rates, and there are different types of learning rate as well. But for now, we will stick with the constant learning rate, and there may be different variable learning rate that varies along with the iterations, and various types of learning rate are there. But we are sticking with the constant learning rate. Okay. Now, so derivative gonna be this. Okay, so this is what I mean by the gradient method. We start with the random w, and we find the gradient at that point, and then we'll move into the right direction. That right means the negative gradient direction at that loss functions. Okay, so now let's define this function first. Okay, so for that I'm defining one called gradient. Defining gradient, I will be using this function to calculate the gradient. I've been given x, and I've been given w, I've been given y. So what will be my weight? What will be my gradient? It just return this expression, uh, this particular x transpose w minus xy. So it's gonna be x transpose w minus xy. Okay, so this will give me the gradient of the function. Now, so let me define the gradient method as well. So I'm calling it a grade descent, and take the x, the y, the training data set, and import the learning rate, right? Eta. Let's call it alpha. I'm defining here as alpha. I'm calling it as eta here, and number of iterations as well. How many iterations you want for this particular algorithm? Okay, that I'm taking as a parameter. Now, so I have to start with some random weight vectors. So I'm starting with the zero weight vectors. You can start any random, you can choose any random vectors. Okay, so I'm calling it W0. So I will just call NP dot zeros. Okay. So how many zeros I want? D plus 1, right? So X dot save 0, the number of features. So this is my initial weight vector. So what I will do, I will just iterate it. I will just find the gradient and then move into the negative direction of that. So for I in number of iterations, right? I in range and iterations. So these are number of iterations. So I in range. I will just keep on W0 minus W0 minus alpha, right? So eta times the gradient, right? Gradient takes the parameter x. Okay, W, so it's gonna be W0 and the parameter y. And once the iterations are done, I will just simply return the weight vector W0. Right? So what I've done, I've started with the random weight vector. Here I'm taking zero weight vector, and every time I'm calculating the gradient at that point and just moving into the negative direction of that, right? That's it. And at last, I'm returning that weight vector. Okay. So for our particular data set, let's see what it comes out. So let's call this function now. Can you mute yourself? Do it again. Yeah. So gradient descent for our dataset X, and the corresponding labels are by train. And eta I'm setting it. Let's try to find out 4 different values. Okay, so let's try to find out one first, and then number of iteration I'm setting to, let's say, 10. Okay, so if I found out the gradient weight vectors using this, so this comes out to be why this is 2 cross 2. Why this is 2 cross 2?
X dot shape of 1.
Hmm?
Yes. Should
X
be X
dot
dot
shape
shape
of
of 1.
in the 36 cell of the
No, it should be 0, right? Number of features. It should be
So
number of features, right?
features, yes, sir, but the features are in columns, no?
Features are in those D cross N matrix we are taking, right?
Okay, the convention is D cross N, right? Okay. Then it should be fine, I
So
think.
NP dot slice 2 cross 2. So this is gonna be D cross D matrix. D cross D matrix. D cross 1, D cross 1. This is okay. This is, let me check. Give me 1 minute, let me check it.
X dot shape is 2. X dot shape 0.
Yeah, 2.
So we need to add as many points in that.
The number of features is the weight vector's dimension, right?
Yes.
So X dot
I'm not
shape
sure why
0
it's
is
coming out
correct.
to be 2 cross 2. Sorry?
X dot shape 0 is correct. That's supposed to be 2. Weight vector is supposed to be 2.
It's supposed to be 0. Yeah. So what is the error in this? Last time I've done this was grabbing correctly. Let me read down that functions here.
Maybe sir, try bracket, adding a bracket to like add order.
It may be the case, but not sure though.
I think the W has a size of 1 cross 2.
The shape of W can be an issue. I think
Yeah, it can
so.
be any shape, but like in the formula, I think to make sure that
2 cross 2. It should be 2 cross 1. It should be 2 cross 1, right? 1 cross 2 or 2 cross 1, whatever. But thing wrong.
Shape of the W is only issue, sir.
Shape of the W.
Shape of W is 2 comma 1.
So np dot zeros will give me p dot zeros with x dot shape.
Your screen is not visible, sir.
Yeah, 1 minute. So np dot zeros will give me. So this is giving me 0.0. So initialization is okay, but then gradient is.
Sir, you are using X and you change X trains or X D plus 1 dimension.
Where did I change it?
Sir, you change. Sir,
Yeah, d plus 1. So d plus 1 becomes 2, right?
I guess, yes, sir.
D plus 1 becomes 2. Let me again run those codes, but I'm pretty sure x was 2 cross 400, right?
Yes.
There was nothing different in this. Let me again run those codes.
So I think W has the dimension 1 cross 2, right? But it needs to be 2 cross 1.
2 cross 1, right? Yeah.
Yeah.
W should be 2 cross 1.
Yes.
Give me 1 minute. Not sure why it's coming out to be different. Okay, you are saying the initialization is W0, is it? 2
Yes,
cross
yes,
1.
yes, sir. Yeah.
Okay, let's reset that. Reset this as well. Okay, that can be a point. Okay, the loss is coming out to be 4.47. Okay, this is fine. Fine. This is also fine. Okay, so you are calling, you want it to be reshape into -1 comma 1, right? Right. Okay, so if I do this now, yeah, now it's coming fine. My screen.
Yeah.
Are you sharing something?
Yeah, give me 1 minute. Let me share it again. Okay, so is it visible now?
No, sir.
Not yet. Yeah. It's blank. Yeah, now it's
It is
visible.
Visible.
visible. Okay. So what was the mistake there? That initialization was of not 2 cross 1 matrix. It was of some different. It was a flattened matrix there. So I've reshaped into -1 comma 1. So it comes into the shape of d cross 1, right? D plus 1 comma 1. Okay. So now the grade. Okay, so let me, so again, so if I run this function for our data set x and bytrain with the learning rate to be 1 and the number of iteration to 10, then my weight vector comes to be -6, and so very high weight vectors is coming. So maybe the learning rate is very high. So what I can do, or say, or I can even find out the loss in this case to check whether what is the loss value, to make sure that our whether our learning rate is fine or not, right? Or the number of iterations, maybe we can change that as well. So let's make predictions using this. Let's call this as some weight vectors. Let's call it wc, call it. Let's call it wz. Now make the predictions for that. So I will make use of those functions now. So predicts by, let's call it by g hat, and this gonna be my predict function. Predicts I'm making on the training data set and using this weight vectors, right? And what will be my loss then? Loss will be simply loss and the actual level by train and the by gt, right? G hat. Okay. Okay, this is small y. So look at the loss here. It's coming out 10 raised to the power 27. It's very high, right? So let's try to add some different learning rate. Let's try to 0.01. Maybe in this case we are skipping the global minima and just going up and up, right? So setting learning rate to be very low, it's reduced down to a great extent, right? It was in 10 raised to the power 27. Now it's reduced down to some point. Let's add some more iterations. Let's say let's add 20 iterations now, or even you can make slower learning rate. Now in this case, loss comes out, drops down to very low value, right? 4.47. It was in the case of the normal, it was around 4.47, something like that. So this learning rate is working for us, 0.01 and 20, right? Okay. So next task is we will plot the loss function versus iterations, right? So we have set iterations to 20. Let's try for different iterations and check what the loss is. Okay. So I'm taking some different iterations here. So let's call it iterations list, or just call iterations to be a list of some iteration. Let's call first iterations 5 iterations, 10 iterations, 15 iterations, 20 iterations. You can set any numbers you want to plot. And okay, so I want to plot the loss function. So for I in iter, what I will do, I will find for every iteration, I will find the loss function. So for loss function, I have to calculate the weight vectors, then the predictions and the loss, right? So I'm calling that, let's call this weights, WTF weights equal to weight. Just make use of those functions for our training data set X, and train labels are by train. Okay. And learning rate I'm setting to be a constant 0.01. You can even draw the plot for different learning rates as well, right? So that will be a good task for you. You can set different learning rates and check how the loss functions behave, right? And iterations I'm setting to I, right? For this weight I will find the prediction. So I'm calling that by the hat, and I'm calling it predict using by train, using x train, and the weight vector WTS, right? And then loss. Okay, so loss I will just store those in a list. So I'm just storing them in a list. I call it loss, loss train. Okay, and okay, so I will just find loss here. So loss function loss takes by train and takes by the at easy codes are here. Just for different iterations, I'm finding the loss functions using those definitions and append those, or store those loss, right? Just to make the plot, will append loss. right? Once I have stored those, I can easily plot those. PLT dot what on the x-axis number of iterations, I will take the iters here, and on the y-axis I will take the loss function. Loss train, sorry. Yeah, so look at very first iteration is loss is coming out very high value. Then it drops down for the 5 iterations, it drops down to somewhere close to 4 point something, and even for the 10 iterations it drops down and it becomes saturated after that. So 10 iterations working fine for this learning rate 0.001, right? Even because this loss function is very simple, and 0 is maybe very close to local, maybe are very close to local minimum. We have initialized our weight vectors very close to that global minimum. That is the one case there where we have for 10 iterations we have reached to the global minimum. In most of the cases where we don't know where the actual weight vectors is, and we initialize it very far from that weight vector, then it may take longer iterations to converge to global minima. So it depends upon the data set and loss function and all. So it's very good exercise to check these kind of scenarios, loss function, how the learning rate behaves, how the number of iterations behaves for different data sets, right? So similarly, you can plot for the test data set as well. We are running out of time. I'm not gonna do for test data set, but the same code will work. Just the where I use X, you can use X test and corresponding labels. The same code will work for the test data set, and you can plot the test loss for number of iterations and test loss plot as well. Okay. Now, so this is one way for finding the weight vector, which is gradient descent. There is one very common version of gradient descent, which is called stochastic gradient descent. That what we do rather than considering all the points for finding the gradient, we only consider on subset of a data points to find the gradient and then move into that direction. So it actually doesn't give the maximum direction of maximum change. It gives it somewhere false direction of that because we are not considering the every data points to find the gradient. We only consider some random subset of the data points, so it will give me some false direction into that direction, and we keep on doing this and we keep on going in that way, and may takes larger iterations, but it will converge to the global minima. So only difference into stochastic gradient descent is that in the stochastic gradient descent we only consider a random subset of the training data points to calculate the gradient rather than considering all the data points. Okay, so that's what we are gonna do here. We gonna call it stochastic gradient descent. Let's call it SGD now. The same parameters x, y, and eta, and what number of iterations. Okay, so same parameters. So initialization gonna be w0 my np dot zeros, and same x dot shape gonna be 0. Again, this I can reshape it into column vector, right? So it's gonna be column vector gonna be -1, 1. So what I will do, I will just take the random sample. So for every iterations for I in enters range. So what I will do, I will just take the random samples, right? So for I have to set the random seed as well, just to make sure that every time I run this code, the answer doesn't get changed. Okay, so I will change. I'm calling RNG as np dot random default RNG. That is some seed point. For I will check set at I. Okay, and I can get those indices to make. I can take RNG dot integers. So it will give me the integers from 0 to n points, right? So because I'm taking the indexes of those data points, so I will start integers from 0 up to the number of samples. So it will be x dot save 1. These are number of samples, and how many I want in a particular batch, I can decide it in the parameters as well, but I'm fixing it to the number of examples divided by 5. So I'm setting it x dot save. So in every batch, I'm considering some 400 times divided by 5, that many a number of examples to find out the gradient. Okay. So what will be my x1 now? So this data set I will consider using the indices. And similarly, I can take the by one as well, the corresponding labels. So it will be my by with indices, right? Now I will calculate the gradient at for these data points, these data set x1 and by1, rather than doing x and by. So what I have done, I've taken some subset of x, right? And for those points, I've taken using this indexes. So these indices are, I'm taking some integers from 0 to n, right? And how many integers I'm taking? I'm setting some 400 times 5. Some 80 examples I'm taking to in a particular batch. Okay. And then I will do the update rule. Same update rule, W0 is equal to W0 minus eta times gradient, right?
So what is RNG here?
RNG is a module. It's called, it's actually stand for random number generator, RNG. So it's a module in NumPy random.default. It's actually used for generating random numbers for some different distributions, right? So this for I'm to generate integers, then I will use this module RNG, this np.random.default RNG. This module for generating integers, there's a function called rng.integers. Right, so this will give me the integers, random integers from 0 to up to this n. This is the number of examples, right? So it will give me some different integers. So this module is used in NumPy to generate some random numbers from different distributions.
So is it same as random.rand int?
Yeah. So that also you can use random.randint to generate the random integers. Yeah, that is again a different base to generate numbers. So there's two different bases in NumPy. One is called this module. This particular module is there to generate numbers, and there is called numpy.random, right? So numpy.random.randint or rand and then some different functions are there. So there's two different modules to generate those numbers. So I think you must have gone using this module as well in the last or yesterday's session, right? Didn't you?
Yes, sir.
Okay. So now I will make use of this data set to find the gradient, right? X1 and Y1. And what was other parameters here? Gradient W0, right? So
Wait.
the W0 was the second parameter, I guess.
Yes, that was the second.
Yes.
Yeah, gradient second parameter was the W0.
Excuse me, sir. Sorry to interrupt. One question.
Yes.
So this is mini batch gradient descent, no?
Yeah.
Because
This is
taking a
batch
subset
gradient
of
descent. Yeah, subset. So there's two
subset of
different
the samples.
three versions are there. One is called vanilla version, which is actually we take all the examples, right? The normal
That
one.
is like
Second is
the
mini batch.
normal, yeah.
Yeah. So there is second version which is called mini batch, where we take some different batches of the examples, right? And there's another which
And
is
in
called
the
stochastic.
yes, sir.
We
Yes.
consider only one data point to update the weight vectors. But
So yeah, in
convention
the
that we
case of
follow is the
SGD, in the case of stochastic gradient descent, I believe we only take one, no? One example.
yeah, we generally take one, and most of the
Yeah.
testing
But
you
in
will
this
find
case, we've taken a subset of that, so I think it is
subset of
more appropriate to consider it as a mini batch one.
mini batch.
Right.
But
Mhm.
so I hope you are from the previous term student. So
Yeah.
this term we have considered stochastic to be taken as a
Okay.
subset of the samples.
Subset.
Okay.
All right. Okay. Understood.
So it's
Sure.
just a matter of conversation. It's nothing different. Okay.
Yeah. Just that
Yeah.
nomenclature thing. Yeah. Okay.
Yeah.
Sure.
So remember, there we take different batches, and in different batch, once we go through each and every example, we call it an epoch, right?
Yes. Yes. That is
Epoch becomes, and then we do epoch wise different epochs for different epochs. Here we don't consider it as well. We just keep a random sample, update the weight, and again take a random sample, then update the weight. There, what we were doing, we take the random sample, and in the next random sample, what we have to make sure that whatever we have already chosen don't come into the second sample. And once we go through each and every example, we call it one epoch, right? Once we have done one epoch, we store the weight vectors, and then we'll start doing epoch by epoch, right? But here we are not doing that. That is, we are taking one random sample, then updating, then again taking random sample and updating. This doesn't. We are not doing any epoch wise here.
Sure,
So
sir.
there
Okay,
are
that's
different
clear.
versions of those
Yeah,
things.
understood.
Okay.
Thank you.
Okay. Yeah. So this is called stochastic gradient descent. There we take only some subset of the data points to find the gradient, and other things are the same as the gradient descent, nothing else. Okay, the same both the things, both things. I mean the drawing number of iterations and loss, or even you can plot the learning rate times loss. So here I've taken iterations, different iterations. You can take different learning rates and then store loss function corresponding to those learning rates and then plot. The same code will work there. Okay, and the same thing you can do for stochastic gradient descent as well, right? Okay, so these are two methods we have for optimizing problem. One is normal method, another is gradient descent method that we have done, and this finishes our linear regression model. If you have any doubt, you can ask. Otherwise, we can move to the kernel regression part.
I have one question. In just the plot which we plotted, just can you scroll up, sir? Yeah, sir. In this plot, sir, once we receive it to point number 5, item number 5, that elbow point.
Yes.
Is it possible that the error increases after that in somehow?
Yeah, of course it can be, because if what happens, it depends upon learning rate. Here we have set the learning rate to be 0.05. Let's say at 5 iterations we have come to the global minima, near to global minima,
Yeah.
and in the next iteration it crosses the global minima. It may happen, and because of the learning rate is high, you can keep on going into the negative direction. It can oscillate, but it may happen that you never reaches the global minima, and increasing number of iterations you can go away from the iterations as well, just because let's say you are in the peak of the peak of the parabola, and you have set you are close to the peak, and you set learning rate too high, then you will go to the other side of the peak, and it may it keep on oscillating just because of learning rating high, and your loss never comes down. So it may happen, right? So in that manner, what you should do, you should keep decreasing your learning rate. If you see that behavior, like loss is increasing by increasing number of iterations, then a better way to do, set different learning rates, or set the less learning rate.
It means this graph can be one good indicative of my optimization of the learning rate.
Yeah. Here this learning rate is very it's working good.
Okay.
Even if you look at the number of five iteration, is loss drops down to 4 point something, right? And just because our weight vector is very close to the global minima.
Yes. Okay. Thank you, sir. Thank you so much, sir.
Okay.
Can you run this SGD?
This code?
Yes.
Okay, if I call this function for our
Yeah,
data set SVD for our data set X by train eta, let's say to be 0.001, and let's iteration to be 10. So weight vectors will come out. What's the wrong? Index 340 is out of bound. Index 340. Where we have taken index 340.
We need to take columns instead of rows. X indices, no? It is taking rows.
Oh yeah.
We have 2 rows only.
Here we have to do this thing. Yeah, correct. That was a good point. Yeah, now this is coming to cross one. So this is your bias term. I mean that intercept, and this is 3.7. And remember your bias in the data set you have added as 4, right? So if you look at the original data set that we have created, it's plus 4, and we want intercept to be somewhere close to it. And by looking at this particular example I am talking about, just looking at the weight vector, you can say that yeah, it can be good one, right? Okay. Okay, if you keep on increasing the learning rate here, I mean the iterations, then you may go far away from that weight vector. Remember now intercept has gone 7 point something. Now it may happen that this will give you the higher loss. So better to stick to the less values of iterations. Okay, and try to do same thing, plotting number of iterations, I've done for number of iterations. You can do for learning rate as well. Okay. Okay, now let's move to the kernel regression part. So
One thing, I mean, when you call this SGD function, what correction you did, because it is throwing the error.
yeah, because last time I've taken x indices, so I've taken rows, but data points are in the columns, right?
Okay.
I'm taking different data points from x, right? So when I call it indices, it will give me the rows, but there is only 2 rows in x, and we want the columns. Dot point. That's why it's showing that index 340 is out of the bound, because there is only 2 rows and we are taking the index at some 340, row at 340. So that was showing an error. Is that clear? So my point is that last time I was just calling 340, this much. This will be throw an error because there is only 2 rows. There's no row at 340 index, so it will throw me an error. So what I have to get the rows at 340, column at 340. Now I will get the example at the row at the column 340. So that was the error it was showing. Okay. Okay. Give me 2 minutes. I will be back, and then we'll start with kernel regression. Okay, so let's move to the kernel regression now. Just give me 1 minute. Okay, so why do we need kernel regression? As we can see in this particular data set, that the relationship of the labels with the features is not linear relationship, right? So in our particular case, our relationship some QB relationship, and the linear functions cannot capture those relationships. So in that case, training error and test error may be higher. So what we actually want them to we want to project the data set into higher dimension, such that those data points come into the linear structure of those features, right? So remember in this case, in this particular case, our feature is only one features x, and the relationship of the labels with the features has some quadratic relationship of some x 2 times x cube plus 3 times x square some plus 4. So what we want to project this data points into higher dimension, or say 3 dimensions, such that now my features become x cube, x square, to x or some constant or x. These features, in these features, this relationship becomes linear, right? Because if this is one feature, this is one feature, then in those features, my relationship of the labels with features become linear. And once we have a linear relationship, we can apply the linear regression there, and our task is done, our trouble is done, right? Because we have projected our data set into higher dimensions so that it comes into the linear relationship. So that's what we want in the kernel regressions. What we do, we just project our data set into higher dimension and then apply the linear regressions. Rather than applying the linear regression on the feature space, we apply into the higher dimension. Okay, so this is the motive of the kernel regressions. So there's one way. You
Please
just
repeat.
uh, so uh, so what I'm saying, you just project your data points into higher dimensions, right? So in our case, I can project my data set into 3 dimensions such that they come into the linear relationship, right? The labels come into the linear relationship with features. But there is a better way, nice way to skip this step. I mean, I will not project the data set, but there's a kernel trick to skip this method. So one way to do that is that you can simply project all the data points. You have n data points, 400 data points. You project all those 400 data points into another higher dimensional space, and then you have now different metrics, X matrix of some capital D cross 400 shape and corresponding labels. Now you apply the linear regression. There is one way to do apply polynomial regression, but in the kernel regressions, what we do, we skip these steps where we don't project the data point, but we can apply the same algorithm in the very nice manner. So we have already done this in the theory part. So I'm not gonna do the proof or and everything. I will just mention the steps, what steps we follow for the kernel regression. Okay, so whole ideas of applying the kernel based on this particular statement. So it says that the weight vectors is nothing but lies in the span of the data points, right? If you want to prove, you can go to the lecture as well. So all the idea of kernel regression lies behind this statement. Weight vectors can be written as the linear combination of the data points. And let's say you have phi transformation where the d-dimensional data points comes to the capital D-dimensional space. And so this matrix now become your phi of x, where x was your original matrix. After the transformation, your matrix become phi of x. So the whole point of apply kernel regression says that your data points now can be written as a linear combination. So this is your linear combination of the data points, where alpha is the coefficients, alpha 1 to alpha n. So weight vectors can be written as a linear combination of data points. Once we have this alpha, I'm done, because and this alpha can be calculated using some bit of algebra. You can equate this to the solution, normal equation solution, that is x transpose w minus xy. So x you can replace with phi of x, and if you do some bit of algebra there, the alpha comes out to be k inverse y, where k is this matrix, right? K is this matrix where this small k is a kernel function from RD to RD cross RD to R, right? So this matrix has this value, this functions. Okay, at the very first entry, it is the kernel function value of x1, x1, and for the second entry, it is the kernel function value for the points x1 and x2. Okay, so this kernel tricks make sure that you explicitly don't transform your data point to the higher dimension. You skip those steps, and this takes care of everything, right? So this kernel function, now we will there are different kernel function corresponding to different transformations, but we are only concerned here only with the polynomial transformation, right? So let's define that function here. I hope you already know this uh, concept of kernel regression. What is this all about, right? So let me define those functions now. So let's call it define. So I'm defining two functions, one for the k matrix for defining this k matrix, and the second for the coefficient, that alpha is equal to k inverse y, right? So definition, I will just for first I will define the polynomial kernel. So polynomial kernel, let's call it polynomial k, and it takes the data points x, and power p, right? Degree, the transformation. So what it should return? What is the polynomial kernel? Polynomial kernel is given by this thing, x1 transpose x2 plus 1 raised to power p. So it will so for this kernel here this will be entry x1 transpose x1 plus 1 raised to power p. This will be x1 transpose x2 plus 1 raised to power p. So simply it is just, it will return x transpose x plus 1 raised to power p. This will give me this matrix, this K matrix, right? Okay, so next function I'm gonna define is for this coefficient vector alpha. So alpha is nothing but K inverse y. So let's define coefficient. It is gonna be takes x and y and the p, the degree. So it's just the K inverse y. So K be already calculated using this function. I can make use of this function definition. Polynomial K for x and p. Once I have this, I will simply return K inverse y. K inverse. So inverse I can write np dot lin alg dot p inverse. I generally go for pseudo inverse to make sure that it doesn't throw any error. For K inverse and by simply by, right? Okay. Now you have this alpha. Now you have this alpha, so you have this W vector. W vector is just a linear combination of this 5 data points and this alpha. So for making predictions, what you do? For making predictions, if you do some algebra there, if you put the values of alpha here, if you and k values as x transpose, x transpose x, you will see that your predictions comes out to be this k xi x dash alpha I, where alpha is this alpha vector, elements of this alpha vector, and let's say you have to make prediction for the test point xt. So what you will do, you will find the kernel function value for xt with each and every data point, I data point, and just multiply with corresponding alpha I, and just take sum over all those points. Let's say some data points you have to make predictions. So what you will do, in the x matrix you have the data points x1 to xn and alpha 1 to alpha n and alpha values you have. So you will find the values of k x1 xt and multiply by it with the alpha 1. Then you find the value of k x1 x2 xt and multiply by it alpha 2. Similarly, you will find the value of k xn xt and multiply it by the alpha n, and then sum over all those values. So this will give me the predictions, right? So this is how you make the predictions. Okay, so let's say you have this training data set for which you are training your model, and this is the test matrix for which you want to make the predictions, right? So what you will, let's say for this particular data point xt, when you have to make predictions. So what you will do, you will find that k value. So k value for each x for corresponding to each xi. So x1 to xn xn. So you will find x1 transpose xt1, x2 transpose xt1 up to xn transpose xt1, right? So this will, so remember this matrix x train transpose x test will what it will give. So because in x train transpose your call rows become x1 x2 xn, and if you do the multiplication of these two, it will become x1 transpose xt1. Similarly, the second entry will become the x1 transpose second column of this, so xt2. So this column will give me the kernel function values for xt1 corresponding to those x1 to xn, right? And if I multiply it with alpha, what will happen? If I multiply this matrix with alpha, I have to make some algebra here, plus 1 raised to power p I have to done as well, but that can easily be done. But if I multiply it with alpha, then what will happen? Alpha means alpha 1 to alpha n.
Prediction.
Give prediction. If I take the transpose, then the columns become these values, x1 transpose x t1. For t1, it comes in the first row. For the t2, it's coming in the second row. If I do the multiplication with alpha vector, then the every entry or every element will give me the prediction for all those test data points, right? So that is what I'm gonna write the function here. So the convention for both the matrix is d cross n, right? So I'm gonna define definitions for prediction. If I'm taking the training data set for the train the model and the corresponding label, let's call it by let's call it by, and the matrix for which I want to make the prediction, let's call it x test, and the power p, polynomial degree power, right? So what I have to do, I have to first find the k, that alpha vector. So what is alpha? Let's call it alpha. Alpha gonna be this function value. This I can call this function coefficient. So coefficient I can call, it can take the matrix x train by and the power p, right? And once I have alpha, I have to find this matrix k transpose x test. That's it. So I will call it k, let's call it k matrix. Gonna be x trans x. So x train times x train transpose times x test and plus 1. I have to do that algebra here as well. So this will become the k matrix, the function value, right? So, and what it will return, the prediction will be what? It's just simply k matrix transpose alpha. K matrix transpose times alpha. Okay. So is this part clear? How this is this matrix times alpha giving the prediction? Okay.
Yes,
Okay. Once you have the predictions, you can find the loss. So let's find out the loss here. So let me call this predictions. Let's call this pi p hat. Call it. So I will use prediction function for I training x train and y train. Okay, this is x. Okay, for remember, when you are applying kernel regression, you need not to add the dummy feature as well, because the kernel, the transformation itself makes sure that you have added dummy features to that. So you need not to add dummy feature explicitly to that. So I'm making use of x train here rather than x. So and I'm to find the loss for the training data set. So I will use x train here itself, and the power I will use, let's say 1. So this is small y. Let's say degree 1. Degree 1 is linear regression itself without any transformation. So if I found the loss here, so loss will be actual will be by train.
Extend we are using twice.
Yeah, one for the remember in this particular function parameters were this one for the modeling, right? Where we find the alpha vector. This is for making predictions. So I'm making predictions for the training data set. Right? So this will become by p hat. If I find the loss here, it's gonna be 4.47. Remember in the linear regression, this was the loss, right? 4.47. 4.47. This was the loss. Trailing gradient, even that for the gradient, it was same, similarly 4.47, something like that.
Will you come again about explain
4.47.
twice?
X train. Okay. So what are the parameters for this function? I've used two parameters. One is x train to model, and the x test here it is the matrix for which I'm to make prediction. Right? If I'm calling this function, this
Yeah,
is
got it. Thank you.
So this is the loss for the training data set. If I have to make prediction for the test data set, I will pass that X test here, right? So X test here I will pass, and then loss will be by test and by P train, right? I've taken degree 1. You can take different degrees. Okay, so remember for the 1 degree you have that this much of test loss, and training we have already calculated. Let's check for degree 3 as the data set follows linear 3-degree relationship with the feature. So in this case the test loss has reduced down to point something 2.1. Let's check for the training loss as well. X train, right? And this will become your Y train.
Nathan, if you're speaking, you're not audible.
I think it's a disconnection. His cursor is stuck.
Hello, am I audible?
Yes, no.
Yeah.
Yeah, sorry, I lost the connection in between. So actually now we are done with both kernel regression and linear regression part. This one code is left, and then we'll move to the regularized version. Quickly we'll look for that. Okay, so because there is only one extra term added in the loss function, that's it. Otherwise, all the codes will be same. We will add only one extra term there. Okay. So one more task you can do is you can find a plot for the different degrees and different loss. So you can, I think you can do that as well. If you want me to code, I can do that. So let's take different degrees. Let's say for I in range, let's say different degrees. Let's say up to 1 to 5. Okay, let's for 5 degrees I'm taking, and every time I'm taking different degrees, I will find different prediction and different. So I will store those loss here. So I will call those as a loss list. Call it equal to some empty list. Now what I will do, I will find the predictions every time, right? So let's call this by equal to prediction for training data set. I train by training data set X training loss I'm considering. Test loss you can also do, and degree is I. Right. Once you have predictions, you can find the loss. So loss will be loss or by train and by head. Once you have this, you can just append this in that list, and you can easily plot. range 5, right? The number of degrees, no, sorry, the degrees, 0, 1 to 5. And so similarly, you can do for the test loss as well. This is somewhere, right? So for degree 1, it is very high loss. For degree 0. Okay, so degree 0 is going very high. Degree 0 means you are learning only the constant, and learning constant is you are making prediction as a mean always, right? And degree 1 means linear regressions. Then degree 2 is reduces down. For degree 3 is again reduced down, and then training loss becomes saturated, something like that. You can also do this thing for the test loss as well, and check the behavior of 4 different degrees, and you will see that it becomes saturated after degree 3. So the degree 3 is the best for this particular data set, right? Okay.
Discussion, sir.
Yes.
But if you go up to a certain point, like again, it will like won't spike, right? So
After some point, what will happen?
like the loss will again like spike up, right?
Yeah, training loss need not to go up, but the after test loss may go high after some point of degree. After some point of time, test loss will go high, but training loss, it may happen that it becomes 0 because it start fitting each and every data point with higher degrees, and training loss will go 0 and become saturated at some point of time, but the test loss may go higher after some degree.
Okay, so it's
That may,
almost like it's overfitting. And
yeah, for higher degree, it will become overfitting then.
okay, all right. Okay.
Yeah. Okay. So if you have any doubts in linear regression, kernel regression, please ask. Otherwise, we can quickly move to the next part, which is regularized version. It won't take much time because it's extra edit term. I will just go through the code. I'm not gonna write those out. Can you give me 1 minute? Okay. So okay, I will quickly explain these codes. It's the same, just extra term added there. So in this particular data set, for this particular algorithm, I'm gonna use this data set. It's present in SQL libraries. You can download it from there. So there's one API called load derivatives. So it's derivatives data set, and this makes sure that it comes into the NumPy format. Okay. So how it is downloaded? Just if you are not sure, you can just skip this part. It's just a data set loaded from different APIs using different APIs. So X will give you the data matrix, and Y will give you the labels.
Sir, would you
So
please share this file?
yeah, I will share both the files, this regularization and linear regression part. Okay, after this session. Okay, so there's nothing much in this particular collab. It's just extra time added in this B2X code. That's it. Right. I'm just gonna explain it. I'll just go through the codes here. Okay, so this is how the data set is loaded. So X you can think as a data matrix and Y as a label vector. So you have to split it into two parts. One is test data set and training data set. So for that, I will shuffle data first and then split the data set, right? To make sure that it's not like first 50 comes into training and last 30 goes to test. So for that, I will shuffle data set. So for shuffling data set, what I can do, I can just take different indices, and then for that different indices, I will I just take the random indices, right? So there's one way to define that is called, let me define that. So do you know about this np dot random dot permutation?
No.
No, sir.
Let me explain that. So np dot random dot permutation. So what it does, it actually gives the different permutations of the sequence provided. If you provide some sequence here, it will give the different permutations here. So if I set 5 here, so it will give me the permutations from 0 to 4, 0 to 5. So it give me one permutations from 0 to 4, 0 to 4. Okay, 0 to 5, 5 excluded, right? So let's say I've given some 10, and every time I run this code, it will give me a different permutations
So
of the
one choice
sequence.
out of 120 possible permutations.
One permutations, yeah, one choice after those possibilities, right? It give me one permutation. Now, if I set this permutations here as a different indices to take out to suffer my data set, right? There's one way to do that, and other is that I just take different indices. So what np.arrange does. So this np.arrange, I've already explained. It will give me the conjugative number from 0 to n, right? So x dot here, and one more thing here, x has the same n cross d, not d cross n, and you can transpose it as well if you want. Okay. So here x dot save 0 will give me the number of examples. So I will take the indices from 0 to n, conjugative number 0 to n. I've already explained what np.arrange does. Okay. And then there is a function called random.shuffle. It's actually it will shuffle those indices. Rather than doing these two steps, you can just simply take np.random permutations up to that n. It will give me one permutation of those sequence, right? And then I will take the data using those indexes. So now doing that, it makes sure that my data got shuffled, right? Okay. Next part, I have to split into two parts. One is test data set and training data set. So I'm using the test size to be some fraction of out of fraction for the test size, right? It takes value 0 to 1.
Sir, just a small doubt. Can we do we supposed to use the default range option in the random for the seed?
Seed you have to set by yourself some value.
Are
Here
we
you can
supposed to
set.
use the default range option?
What is default value? I don't remember. What is the default
Default
value
range,
for?
sir, in the previous collab only you used that range option. Default underscore RNG.
Yes, you can go for both manner as you wish. Doesn't matter.
Okay,
You
so
can get
this seed will
different.
this seed is set globally, right?
Yeah, it's set globally at 0.
Because in the morning session, ma'am told that the np.random.seed work for the particular cell only. So I got confused.
No, you can set by yourself. If you want to set some random seed here, you can set here as well in this particular definition.
Okay, thank you.
So what this function does, first is shuffle the data using that function definition, shuffle data. Now test size is given. So length of by into test size will give me the number of data points into test data set, and the total data point minus test data points will give me the number of training data points, right? So test size is this one. So this is the fraction of the number of test data points. So total data points into the test size will give me the number of test data points. And if you separate it from the total number of data points, it will give me the number of training data points. So what I will do in the shuffle data set, I will take the first data points as the training data points and the remaining as the test data points. Similarly for the corresponding label as well. So by shuffling, it makes sure that your data from the original data is not like first 80 goes into train and last 20 goes to test. It's like we have already shuffled your data points, right? That's why we have defined the shuffling of data point. If you don't want, you can use first 80 for training and last 20 for the test data point. That also works. Okay, and it will again return those training data points. For in our case, we have x and y data points, and we have set the 0.25 as the 0.25 as the test size. So if there are 100 examples, 25 goes in the test data set and remaining 75 goes into the training data set. So in our data set we have some, I don't know how many data points, but yeah, for training we have 332 examples with the 10 features, or in the test data set we have 110 examples, right? So now we are gonna apply the rigid regression over this data set, right? Now adding the dummy features we have already done. Column stack, where because here is the shape of n cross d, not t cross n. So we are doing column stack and then transposing it. Now it comes into the d cross n shape, right? If you want to transpose first and do row stack, that is also the same thing. Okay, so now it comes into the d cross n shape, right? Because we have added the dummy features and then taken the transpose of that. Okay, so weight we have already defined. This is the normal linear regression model, not the regularized one. So that's already been defined, right? In the previous collab. And mean squared errors, similar to RMSE, we didn't take the root here. It's just the prediction we didn't define explicitly, just defined the loss function itself, right? X transpose W is the prediction. This is the actual label, and then that mean of that, right? So it's just mean of this thing, X transpose W minus Y whole square, right? So this is the training error for this and the test error for this. You can also find the root mean square error. So both are the different valid evaluation criteria: mean square error or the root mean square error, whatever you want. Right? So now let's move to the ridge regression. In the regression, remember only one term extra added, which is lambda times time size. So this is x transpose x plus lambda time size. So lambda is the hyperparameter, regularization parameter, lambda L. Okay, so it is taken as a parameter here in this definition function, and this is np dot I will give you the identity matrix, right? So if you want to know what it does, so np dot I it give me the identity matrix. I think you have already seen this. If you set 3, so it will give me 3 by 3 identity matrix. Right. So this give me the 3 by 3 identity matrix. So this is lambda into I. I will be my that matrix, identity matrix of the shape n cross n. Right? Sorry, d cross n, d cross d. Right. So this is your ridge loss, ridge weight. That's it. And you can use the same thing for loss function. This weight for the loss function, and you can find the training loss and test loss as well. So in the ridge regression, only one thing is extra added, which is called regularized regularization here, which is lambda times I, and all those functions goes in the same manner, right? And why we have done into the different data set? Because in the previous data set we have only one features, and ridge regressions make sense only when we have different number of features, and features are tends to associated with each other, right? There's some correlation within features. So in that the ridge regressions is significant. Otherwise, if there is only one feature, then why to apply ridge regression, right? So that's why we have taken different data set here. We didn't work over those data set. Okay. So I think this part should be easy. I just gone through this just to make sure that it is a part of your, it's gonna be a part of your OPE as well, right? So in the OPE you will be having linear regression and regularized linear regression and color regression for this particular session.
Sir, I am not that much comfortable with the kernel regression. From where I can read this about, because for the first time I am reading this kernel regression.
So have you seen the Professor Arun's lecture?
No, sir, actually I cleared this MLT, I think, second term. So I
Yes.
think after
So
that,
the best resources is to go through the Professor Arun's lectures of about kernel regression, week 5. You can go through the week 5, second half of the week 5. So
is
this,
there a way I can get the PPT, because I am not enrolled to that course, so it is not accessible to me.
PPT. Okay, I'll ask the team if it's okay to provide those PPTs
Go through
to
YouTube.
the STEM students. I think it's already shared with everyone, right?
If it is
Yeah,
okay,
the lectures are
I can
already
share
available on the
the
YouTube,
link.
guys.
And
Okay.
Lectures are available. I'm not sure about the PPTs.
and PPT won't be much help. I mean, you have to go through the video.
Yeah. Obviously, if you want to learn something from the PPT, you have to go through the lecture. Otherwise, those PPTs won't make much sense.
Okay.
It's a different way of the polynomial transformation. There we have projected our data set into the higher dimension and then apply the linear regression, right? Here we skip that part and apply the kernel trick. Okay, and I don't remember any standard book that covers the kernel regression. I've seen it doing only Professor Arun does this. So not sure about the textbook and any other resources. So it's better to go through those lectures. It will be available on the YouTube.
I think Karthik sir also explained like last to last term kernel this part week 7 or week 8. I don't remember.
So that is kernel SVM. I think he must have explained.
Yes.
Kernel SVM, but not for the regression part, right?
Yeah.
He must have done it for the
But
PCA, kernel PCA, and
yeah,
SVM kernel
given a
kernel
little
SVM.
idea, but not explained too much. And refer some book written by I don't remember
Yes,
the
for
name.
SVM, you may find in the any standard textbook. For kernel SVM, you can find in the any standard textbook, and for PCA as well. But for regression, you generally don't find in any standard textbook. It generally follows by polynomial transformation, where we transform the data point and does linear
So,
regressions.
is it done now? Can we leave?
Yeah, sure, you can.
Thank you.
Okay, so this is all about for this particular session. There will be 2 more sessions tomorrow. Please do join those sessions, and I think we can drop off now. Thank you everyone for
Sir,
joining.
can we know the topics for tomorrow?
Tomorrow is gonna be perceptron and SVM.
Okay. And bagging and boosting algorithms, we are not going to
No,
see.
it won't be covered here, but you can do by yourself. For the OPE, it won't be there. So in OPE, only those topics will be there which are covered in the workshop.
Okay.
Sir,
Thank
when can we get graded assignments?
It's already been provided, right?
Sir,
No,
where, sir?
sir.
No, sir.
So course details are not given.
Not given. Okay, I asked the concerned team to make it public. I'm not sure whether I think it
A
must have
request to
done by
send, a
now.
request to ask someone to send a separate email with all the links regarding this workshop.
Okay.
Sir,
So
we have
one
not
is
received
for
the
that Google Drive
assignment link
link,
also.
right? Assignment will be provided. I think it must have been provided by now, but I'm not sure why it hasn't been. So I will ask the team to make it public again, and this drive is already shared with you where we have added this collab files. I will add this regularized version collab file as well, and then you can start working.
What will be the pattern of OPE? Like,
Same as the assignments.
Sir,
Then
assignment will be in some portal or because those students who are not enrolled in the MLT course this term.
you all will be enrolled for that. The workshop, whoever has registered for workshop will be enrolled for that.
One more thing, sir. Is there any minimum marks requirement for assignments?
Minimum marks I'm not sure about, but attending assignments and 90% attendance for these workshops are required for eligible.
I think 50% is mentioned in the email.
Yeah, 50% is it?
It is for OPE,
It is for
not
OPE, but not sure about the eligibility for attending OPE. But it's like attend those assignments. Okay.
If I had not attended last Friday session, will I be eligible for the OPP? I attended both the sessions today, but yesterday's session I missed out somehow. So will that be marked
So
as
the criteria is you have to take 90% attendance, right? So 90% means if there are 2 hours and 5 sessions, 5 or 6 sessions, 5 sessions, so 10 hours. So 90% of that 10 hours you have to attend.
Okay, thank you, sir.
your attendance will be reported. Last date will be 21, I guess. If it's not shared with you on time, then we may extend. Otherwise, it's gonna be 21. Okay, so assignments are not much different from the assignment that we have provided weekly. So that's why we have don't keep the deadlines we didn't give much time for that. So you will be provided 3 or 4 days for that. Okay, so only 3 or 5 assignments you will not 3 or 5. You will be provided 5 assignments, I guess, 5 or 6. Okay, so based on all those questions will be based on this workshops, nothing else. Okay, I'll ask them to make it public as soon as possible.
Okay, thanks for the session, sir.
Okay.
Thank you, sir.
Thank you.
Stop it now.